Okay. Then let us start with Gauss-Seidel iterative method, right. So, for that we will consider a 4 bus power system, right, and this is bus 1, bus 2, bus 3, bus 4, this is generator 1, generator 2, and for this your diagram, right, generally for all generators have their transformer, right, after that connect to your high voltage your what you call that transform from the terminal voltage to the other side is high voltage side, then transmission line, but we will not show here a transformer for the time being, right, but later the transformer modeling will go for that, but for the time being here you assume that this kind of diagram, no transformer showing here, right. So, this is generator 1 and this is generator 2 and bus 1, 2, 3, 4, right. So, in that case and loads are shown, right, and transformers anyway, that generators, then you have a step up transformer, they connect to the line, this is not considered here. Later I will give you the transformer modeling. Basically for transmission line, transformer also can be represented by pi modeling. So, we will see at the end, right. So, but for this it is like a classroom exercise. So, take this and these are the loads are given, and for PQ bus, PV bus all will be explained later, right. So, this is a 4 bus power system, but we have to write. So, we have to see that how we can solve using Gauss-Seidel iterative method, right. So, this bus 1 you consider as a slack bus, right. So, S is equal to 1, S stands for slack bus, S is equal to 1, right, and that means here bus voltage and magnitude and its angles are known, right. So, in this case there is a 4 bus problem 1, 2, 3, 4. So, n is equal to 4 and slack bus we define S is equal to 1, right. So, from equation 11 we can write like the equation 11 that is this one, this is your equation 11, the same equation we are actually rewriting. This is actually equation 11, this is equation 11, right. Same equation we are rewriting, that your V I is equal to 1 upon capital Y I I in bracket P I minus J Q I upon V I conjugate minus sigma Y I k V k, k is equal to 1 to 4, but k not is equal to I is equal to 1, 2, 3, 4, but I not is equal to slack bus, that is I not is equal to 1, because slack bus voltage actually known to you, right, voltage magnitude and angle both are known to you. So, voltage is known to you, therefore, if you write V 2 equation, because V 1 is not required, because voltage magnitude and angle is known. So, V 2 is equal to, that means when I is equal to 2, so V 2 is equal to y 1 upon capital Y 2 2 from this equation only, P 2 minus J Q 2 upon V 2 conjugate, right, then minus sigma k is equal to 1 to 4, I is equal to 2. So, it is y 2 k V k, right, because I is equal to 2, that is why P 2 minus J Q 2 upon V 2 conjugate and I is equal to 2. So, capital Y 2 k V k, k not is equal to 2, because k not is equal to I is equal to 2. So, k not is equal to 2, right. So, if you expand this one, V 2 will become 1 upon Y 2 2 P 2 minus J Q 2 upon V 2 conjugate minus y capital Y 2 1 V 1 minus capital Y 2 3 V 3 minus capital Y 2 4 V 4. Similarly, when I is equal to 3 in this equation, when I is equal to 3 you put and k not is equal to I means k not is equal to 3, right, you will get V 3 is equal to 1 upon Y 3 3 and P 3 minus J Q 3 upon V 3 conjugate minus Y 3 1 V 1 minus Y 3 2 V 2 minus Y 3 4 V 4, all capital, again and again not uttering capital, right. So, similarly, V 4 is equal to 1 upon Y 4 4, that is P 4 minus J Q 4 upon V 4 conjugate minus capital Y 4 1 V 1 minus Y 4 2 V 2 minus Y 4 3 V 3. These are V 2, V 3 and V 4, 3 equations, because 4 bus problem, bus 1 is a slack bus, right. So, how one can make it? Now, in the Gauss-Seidel method, the new calculated voltage at P plus 1 iteration, right? P is the iteration count, right. P is the iteration count at P plus 1, that is V I P plus 1, immediately replaces VIP and is used in the solution of the subsequent equation. That means, what I want to mean before coming to this, that suppose you have got this equation V2, V2, V3, V4, these three equations you have got it, right. Now, when you are solving this, suppose first you are computing V2, right, then you are solving V3, then it V4. Suppose initially all the initial values of V2, V3, V4 are known. So, one can do is like this, V2 is equal to put all the initial values, you can get it, V3 is equal to all the initial values you put here, you get V3, and V4 all the initial values you put, you get 3. But in that case what will happen, that computational time will be more and number of iterations will be more. That is why what we do actually, that first you calculate using all the initial values of V3, V4 and P2, Q2, all these things are known, right, and then you get the V2. But whatever immediately whatever value of V2 you get in this equation, whatever V2 you got in this equation, put this value and other value, other initial values you put, right. Whatever you got V2 in this equation, V2 is here, do not take the initial value, this value directly you put, but V4 initial value you have to take, because V4 is not computed here, right, and this in equation is also independent of V3, because according to our connection, that your according to this line connectivity, right. Now V2 is computed, V3 is computed. Now, in this equation V2, instead of taking initial values of V2 and V3, V2 you have computed, V3 you have computed, both you use this, right, such that your acceleration, your convergence acceleration will be faster, right. That is why that meaning is that you that immediately replaces VIP and is used in the solution of the subsequent equation, such that your convergence will be faster, right. So, that means in terms of iteration, P is the iteration count, I can write this equation, I mean this equation, this V2 equation I can write in terms of P, right. That means your V2 P plus 1 is equal to 1 upon capital, these are parameters, 1 upon capital Y22, P2 minus JQ2, these are known, right. And here I am writing V2 P conjugate, right, because here whenever I use this, I have to use the initial values, right, initial values. That is why instead of P plus 1, I am writing V2 P conjugate, right. Then minus capital Y21 V1, V1 actually known 1 plus J0, generally angle is 1 angle 0, 1 angle 0. So, do not put P here, no need, right, minus capital Y23 V3P minus capital Y24 V4P, P is the iteration count. Here you have to take the initial value. In the next iteration, that V3 P plus 1 y upon capital Y33 P3 minus JQ3, it will be V3 P conjugate, as I told like V2, right, it will like that, minus y capital Y31 V1 minus Y32, do not write here V2P, because this V2P plus 1 already computed from here, you make it here, right. So, it will be V2P plus 1. Similarly, V4P plus 1 equal to 1 upon capital Y44 P4 minus JQ4 V4P conjugate this thing, and here V2P plus 1 V3P plus 1 both have been computed. So, here you make minus Y42 V2P plus 1 minus capital Y43 V3P plus 1, such that your convergence will be faster and number of iteration will be less, right. So, that is why this way one can solve. Now, algorithm other things will come later, right. Now, you note that bus 1 is a slack bus, right. So, under normal, now starting values how we will take, that we have to discuss. So, under normal operating condition, the voltage magnitude of buses are in the neighborhood of your 1 per unit, right, that is 1.0 per unit, and or close to the voltage magnitude of the slack bus, right, whenever you solve it. So, an initial starting voltage 1 plus J0 for unknown voltage is satisfactory, of course, right, and the converse solution correlates with the actual operating states. So, these are the thing. Now, calculation of the net injected power, right. So, from equation 11 again we are rewriting equation 11, right. So, in this case just hold on. So, you have to find out the expression of Pi and Qi, right. So, calculation of the net injected power. because when you solve the load flow, this calculation P I and Q I separate expression is needed, right. So, because in load flow that the injection P I and Q I injection for P Q bus say that it will be that schedule value will be given, right, but this P I and Q I you have to calculate also iteratively and you have to go for checking the mismatch. So, that is why this P I and Q I both you have to find out its expression. So, that is why equation 11 we are rewriting P I minus j Q I upon V I conjugate is equal to capital Y I I V I plus your k is equal to 1 to n y I k v k, k naught is equal to I, right. So, this equation that means P I minus that means from this equation only that P I minus j Q I you can write V I conjugate, right, capital Y I I V I plus k is equal to 1 to n capital Y I k v k, k naught is equal to I, right. So, this is equation 13. Now, define this Y matrix admission element, all the admittance element in terms of its magnitude and angle. Therefore, that Y I I you write more magnitude of Y I I angle theta I and capital Y I k magnitude or Y I k angle theta I k, right. Similarly, V I is equal to magnitude V I angle delta I. Therefore, V I conjugate will be magnitude V I angle minus delta I. Similarly, V k is equal to magnitude your what you call V k angle delta k, right. That means, all this value this Y I I, V I, V k all these things you can substitute here, right. If you substitute here all these things that V I is equal to magnitude conjugate is equal to your magnitude V I minus delta I, V I is equal to magnitude V I angle delta I and simplify, you please simplify this one, right. What you will get P I minus j Q I, right, and first one I am showing it that this first term that is your V I conjugate then Y I I and V I. So, this V I conjugate actually it is V I angle minus delta I and Y I actually magnitude Y I angle theta I, right, into your magnitude V I and its angle is delta I. So, magnitude V I means magnitude V I square, then magnitude Y I and this angle theta I, because this delta I minus delta I plus delta I will be cancelled, right. So, that means similarly your second term in that you substitute all these values, you will get this first term will be now coming magnitude V I square magnitude Y I angle theta I. Second term k is equal to 1 to n, k naught is equal to I, magnitude Y I k, then magnitude V I angle V k, then angle it will be theta I k plus your delta k minus delta I, this angle, right. Now, this angle theta I k plus delta k minus delta you write cosine theta I k plus delta I k minus delta I plus j sine theta I k plus delta k minus delta I. So, if you write this one you will get P I minus j Q I is equal to magnitude V I square Y I cosine theta I plus j magnitude V I square Y I sine theta I, right. This is the first term, these two terms, and second term also one real one your complex part. Similarly, second term also one real one complex part. So, k is equal to 1 to n, k naught is equal to I, Y I k, V I V k, these are all magnitude, not telling again and again, cosine theta I k plus delta k minus delta I plus this is j, k is equal to 1 to n, k naught is equal to I, then Y I k, V k all magnitude sine theta I k plus delta k minus delta I. This is equation 4. Now, from this you separate real and imaginary part, from which you will get P I is equal to and Q I is equal to separate, right. Then you separating real and imaginary part, P I you will get that magnitude V I square magnitude Y I cos theta I plus k is equal to 1 to n, but k not equal to I, magnitude Y I k magnitude V I magnitude V k cosine theta I k plus delta k minus delta I. Similarly, that means this one, right, look, this term is out of this is ith term, it is out of this sigma, right, summation, but k, that's why k not is equal to I. Now, if we want to include this term in this, right, in this term, that will be k is equal to 1 to n v I v k y I k cos theta I k minus delta I plus this term is taken inside that, although it is cos theta I, but when it is when your what you call, when k is equal to I, when k is equal to I, so this delta I will be cancelled, right, then cos theta I will be there when k is equal to I, and when k is equal to I, that v I square and y k is equal to y I will be there. So, v I square y I cos theta I, when you take into that, it will k is equal to 1 to n, right. So, take this term inside this sigma and remove this, right. Similarly, minus q I is equal to this term, that imaginary term, minus your minus q is equal to v I square y I sin theta I plus that y I k v I v k sin theta I k plus delta k minus delta I k not is equal to. Similar way, this term you take into this summation, because this is ith term, you take into the summation. So, in that case q I will be minus k is equal to 1 to n magnitude v I, magnitude v k, magnitude y I k, then sin theta I k minus delta I plus delta k. This is equation 16. This 15, equation 15 and 16 we have to recall again and again. This, that means power expression for power injection P I is equation 15, very easy to remember, k is equal to 1 to n v I v k y I k cos theta I k minus delta I plus delta k, and q I is equal to minus k is equal to 1 to n v I v k your y I k sin theta I k minus delta I plus delta k. So, this is 15 and this is equation 16, right. Now, I hope this is this you have understood, right. This simple thing, only little bit of practice, right. Now, consideration of PV buses. Now, in Gauss-Seidel method or Newton-Raphson method, Newton-Raphson will come later. So, Gauss-Seidel this thing, this PV buses, for PQ buses, the real and reactive powers Pi schedule and Qi schedule both are known for PQ buses. Later we will see how to compute, right. And starting with the initial values of the voltages, set of voltage equation can be solved iteratively using this Gauss-Seidel method. We are talking about Gauss-Seidel method, but for the voltage control bus, the PV bus, right, where Pi schedule and Vi are specified, that means P and magnitude, voltage magnitude are specified first, that means first are specified. So, first equation 16 is solved for Qi P plus 1 iteration, that means this equation, because at the PV buses that your P and voltage magnitude both are known and Q and angle voltage angles are not known. So, in that case this equation that is equation 16, this equation when you are considering PV buses in Gauss-Seidel method, this equation you can write in P plus 1 iteration. So, in that case we can write Qi P plus 1, that is P is the iteration count, is equal to minus k is equal to 1 to n. So, instead of Vi we are putting magnitude Vi P, pth iteration, magnitude Vk P, Yik is the constant, it is admittance matrix. So, no question of P anyway. This sin theta ik is the angle of Yik, sin will remain constant, but delta will vary. So, minus delta Ip plus delta Kp, this is equation 17. That means, this is required actually for PV bus consideration in Gauss-Seidel method, computation of this one require fast, right. That means, then set of voltage equation are solved. After getting this, this set of voltage equation are solved. So, however, PV buses, since Vi is specified, right, in the PV bus, right, only the imaginary part of Vi P plus 1 is retained and real part is selected in order to satisfy this thing. Actually, suppose if ith bus is PV bus, right, my objective is to make the voltage magnitude remain constant, right. Therefore, this in general that your this thing that V is equal to, in general you can write E plus Jp, right. But if in the case of ith bus, you can write Vi is equal to Ei plus it is your this thing Jfp, right, sorry Jf, right, E plus Jf, right. That means E plus your jfi, right. So, this way you can write, and for I and for any iteration, say your this thing you can put in that iteration number. So, Vi is equal to Ei plus jfi. Generally Ei is much higher than Fi. Fi is very small, because voltage angles in transmission system is quite small, right, compared to this thing. Your this Fi is quite this thing or small compared to Ei, right. So, in this case, that means my voltage magnitude remain constant, that means Vi is equal to root over Ei square plus Fi square. That means I can write in other way that Ei square plus Fi square is equal to magnitude Vi square. This one I can write. That means that means that p plus 1th iteration we can write this one whole square plus Fi at p plus 1 iteration whole square is equal to magnitude Vi square, but magnitude Vi remains constant. No need to put p here, because PV bus's voltage magnitude remain constant, right. That is why this that is why you can write this your PV bus case, that Ei p plus 1 square, p plus 1 is that iteration count at p plus 1th iteration plus Fi p plus 1, this also square is equal to magnitude Vi square, but this voltage magnitude remain constant, right. So, in that case what will happen, that when we will do this we ultimately this one whatever we vary that is different thing, but this voltage magnitude has to be made, or what you call that voltage magnitude has to remain constant. Otherwise, in the Gauss-Seidel method we want to include the PV bus. So, this voltage magnitude remain constant. What we will do, that you in this whatever we get, only the imaginary part is retained and real part is selected in order to satisfy. That means, from this equation when you solving Gauss-Seidel method for the PV bus case, when we will come to the numerical, we will know from the PV bus case, first we will find out, suppose for example bus 2 is a PV bus, right. In that case, the way without considering your what you call PV bus, the way you are solving, you solve for V2, right, you are solving, but we know this condition is actually has to be satisfied. Voltage magnitude of V2 remain constant, if it is I is equal to 2, V2 remain constant, but after getting V2, the imaginary part will be your what you call imaginary part will be retained, and new values of this one will be computed, right, such that voltage magnitude will remain constant. This way we will follow. So, that means that your Ei p plus 1 is equal to voltage magnitude Vi square minus Fi p plus 1 to the power half, that is square root of this one, that is equation 19. So, Ei p plus 1, that is p plus 1 is a real part of Vi p plus 1 and Fi p plus 1 imaginary part of Vi p plus 1, right. So, in that case when I will solve this one our numerical, then this thing will be clear. That means, in general way we will find that what is the V2, but that is not exact V2, because we have to maintain the voltage magnitude. That is why in that case that imaginary part will be retained and real part of the voltage will be computed using this equation, and that voltage will be taken such that magnitude will remain constant, right. So, this is the idea for the PV buses. So, when I will take one example later, first the theories and next we will take the example, right. So, and when I will solve those things, all the time we will recall this thing, and everything I will tell you. In between, if I try to solve this thing, then that your hot continuity will be lost, right. Next is the convergence procedure. Convergence procedure is something like this. Suppose you have your n bus problem. Suppose 1, 2 up to you have n number of bus. Suppose your bus 1 is a slack bus, right. That what you will do, that you calculate that voltage this one delta V2 in the Gauss-Seidel method. There are different ways of convergence So, delta V2 you can write that current iteration value V2 p plus 1 minus V2 p, this one you made. Similarly, delta V3 is equal to you make V3 p plus 1 minus V3, this is p. This way up to nth bus you make delta Vn is equal to mod that Vn p plus 1 minus Vn your p, these are all magnitude, right. V2 p plus 1, V2 p, these are all complex. Then you take the magnitude of this one, after differences all the magnitude you are taking them, and they are all real quantities. So, once you this, then after that what you do, you take delta V max, that is maximum, that is equal to max of delta V2, delta V3, then up to delta Vn, right. That means, all this you have computed, then maximum of all these values you take, and if this delta V max, if delta V max some less than equal to epsilon, then solution has converged. You assume epsilon may be 10 to the power minus 4 or 10 to the power minus 5, that depends on you up to the accuracy, right. That means, what you are doing, that we found that difference of delta in every iteration, you have to see this difference, the current value and the previous iteration value, V2, V3 up to Vn, and magnitude you take, and out of which you take max of this one. If the max of this one is less than epsilon, out of this you find out what is the maximum of this, and if that is less than epsilon, then solution has converged, because if max of this less than epsilon means all other or other differences also less than, I mean this other thing all are less than epsilon, right. So, that is the convergence criteria. That is why this in general I have written that delta V is equal to max of Vi p plus 1 minus Vi p mod, and I is equal to 2 3 up to n, because bus 1 we take as a slack bus, right. So, and if delta V less than epsilon equal to epsilon, then solution is converged. You can take epsilon is equal to 10 to the power minus 4, that is your 301, or 10 to the power minus 4 may be considered, right. So, in that case you can get the your what you call that solution thing. This is one way of convergence criteria, right. This is one version. Then another one is that you take del p is equal to max of pi calculated minus pi schedule. That means, this pi schedule value, this one actually known to you. When we will take the numericals, we will know, right. This is equation 21, and pi calculated value you have to calculate using equation 15, that expression we got now for pi later will come, right. That equation 15, and take the absolute of this one, right, absolute value, and take max of that. That means, for all the buses except slack bus like delta P2, delta P3 up to delta Pn, and you have to take the max of that, right. And it is something like this. Just one I am showing that delta P is, suppose delta P2 is equal to absolute P2 calculated, right, minus that P2 schedule value. Similarly, delta P3 is equal to take again P3 calculated minus P3, not writing schedule, but making dash dash dash, right. So, similarly, this way you will take delta Pn is equal to Pn, that calculated value, minus Pn a schedule value, right. So, out of this again you do same as before, the way you do the voltage, delta P max is equal to max of delta P2, delta P3 up to delta Pn, you take max of that, right. So, similarly, your delta Q also. So, that means, this is the meaning of this equation, right. Same is applicable for delta Q, same way, and then you take this one minus this one, and if both delta P and delta Q together, if they go for below your less than equal to epsilon, then you take the solution has converged. Both delta P thing and delta Q both together should be less than, solution has converged, right, both together. In this case, epsilon may be taken again as 0.301 to 10 to the power minus 4 or 0.401 10 to the power minus 5, depends on the accuracy, right. So, this is how one can, these two ways of convergence characteristic I told you, right. So, thank you, next will come.